This is Dan Alford with ARC Specialties. For the last year and a half, we've been working with Hypertherm to push the envelope for plasma robotic 3D cutting. We recently had a request to try to replace a laser cutting operation with plasma, but the dimensional requirements on the hole were plus or minus 5/1000ths of an inch. We're going to demonstrate that for you now.
To achieve this level of precision requires a combination of Hypertherm high-definition plasma equipment and process parameters optimized for each portion of the cut.
Let's see that again from a robot's perspective.
We have broken the circle into small segments to allow us to compensate for robot accuracy and simultaneously change process parameters in real time.
Now to the Metrology Lab to measure our results.
So now we're in the Metrology Lab. Henry's going to use the ferro arm to take a number of hits on each of these circles. He's trying to find the best fit for the diameter of these holes as well as the circularity. Now this is a multi-step process. What we found is the robot accuracy wasn't quite up to our needs on this one, but we're using the data that Henry's generated to optimize the robot's path. That's what the point of this video is. This is a unique case for cutting. The customer needed accurate holes. Now the position of the hole, the tolerance was much looser. So we were able to spend all our time optimizing the cut diameter, and we've achieved the goals on this project. Here's a copy of our software. It's quite extensive, but this is what it takes to compensate for the idiosyncrasies of the plasma process and the inaccuracy of the robot and create a perfect hole. So here are our inspection results. We were just under 0.003 of an inch off on diameter and right in the middle of the circularity limits. One of the common questions we get on robotic part cutting is exactly how accurate can we cut a part? And so I'm going to stick my neck out today and put some numbers on this. I expect to start a few arguments, so leave your comments below. These are the issues that I consider to be significant in accuracy, and then I'm going to give you my estimates of best and worst case as well as typical case, and the best case is this example we used today, which is cutting holes where we're only trying to achieve circularity and diameter. So let's start out with robot accuracy. A best case on robot accuracy is around 0.005. I'm using all imperial units here, and that is with arm mapping, or the case you just saw where we're actually changing the process parameters on the fly. Worst case, I'm saying around 0.090 of an inch. Now robot repeatability is always better than accuracy, and we use that while we're doing hole cutting, because once you set up these hole cuts, where it's actually a case of repeatability more so than accuracy. And so fortunately repeatability on robots is always better. Tool point accuracy. Now this is an operator problem. If the operator manages to either not set the tool center point accurately or damage it on the fly without correcting it, it can account for up to 0.5 of an inch. I've seen worse than this in some applications. And then you get to plasma consumables. Ultra high definition plasma consumables are accurate within 0.001 of an inch. And then I'm saying 0.090 of an inch. That's a case where you've allowed the consumables to wear well beyond where they should have been changed, but it happens in production. So that's why we've left that as a worst case scenario. Then fixturing. If you fixture these parts accurately, they could easily be held within a thousandth. But let's say your parts are castings or something that's not accurate to begin with, and you really can't fixture it. So that could add up to an inch of inaccuracy on your part positioning for your cuts. And then finally, optimizing the path for plasma cutting. As I said, we're actually using multiple parameters as we're going around this part. If you do that, you can virtually eliminate the issues you have with plasma cutting. And if you don't, you can add, I would say, approximately 1/2 of a kerf width or more. And then torch height. You either need flat parts or you need some type of adaptive control to maintain torch to workpiece distance. If you don't, this will affect your part, and it gets worse with large part sizes. So that all totals up to, you can either achieve somewhere around 0.005 of an inch, and then in my worst case here is almost 2 inches. That's pretty bad, but it could happen. So particularly if you have something wrong with your fixture or your tool center point. So let's take a typical case on a large part. I'm saying about 0.020 of an inch for the robot accuracy, maybe 0.002 for repeatability. So again, if you're going to check for the overall positioning, look for 0.020. If you're going to look to see how accurate the parts are part to part, it'll be 1/10 as much, 0.002 of an inch. We're going to assume your TCP, your tool center point, is pretty close. Your consumables are changed on a regular basis, so maybe 30 thousandths. I'd like to hope it's less than that, but people tend to leave their consumables in a little longer than they should. Fixturing, we're going to give your fixture guy credit, assume he's going to hold everything within 30 thousandths. Let's not optimize the path. That's kind of new technology, so not many people are doing it yet. And then torch height, that'll end up, so we're up at about 3/16 of an inch, a little over an 8. We ought to be able to do better than that, but I'm just going to use this as a typical. If you can live with this, you can definitely plasma cut your parts. If you need something better, yeah, it's very doable. But then let's take this special case that we talked about today. Since we're working on just circularity and diameter, all of a sudden the robot accuracy is very, very tight. We're down to 0.5 thousandths because we programmed out any inaccuracy. Repeatability, once again, very tight, 0.5 thousandths. TCP, we worked hard to maintain that accurately. Plasma consumables, we're down at the low end of that. Fixturing, why did I put 0 here? Because in this case, we don't care where the hole is located. We care about circularity and diameter, so we don't get any contribution from fixturing and accuracy. And then we've optimized the path for cutting. We're changing parameters, gas flow rates and such on the fly to eliminate any taper and such, so adding very little there. And we have automatic torch height control. So in theory, I think we should be able to hit plus or minus 4.5 thousandths, and indeed that was we came close to that number. And so this is the chart that I would recommend you consider when you're deciding whether or not to plasma cut parts. Are your tolerances within the technical capability of plasma? This is Dan Alford with ARC Specialties. At ARC Specialties, we thrive on problems. Send us yours.